Welcome everyone. Thanks for coming out tonight to this workshop on heat pumps. My name is Paul Cameron and I'm the director of Brattleboro Climate Protection, which is a nonprofit organization that works closely with the town of Brattleboro to reduce carbon emissions through increased energy efficiency, renewable energy, and sustainable transportation. And this is the latest in a series of workshops that we've held on various types of energy technologies. And we were very fortunate and happy this time to team up with the Sustainable Energy Outreach Network and Guy Payne to put on this workshop. And I also want to thank our other sponsors, the Marlboro Graduate Center, Brattleboro Savings and Loan, River Valley Credit Union, and also thanks to BCTV for taping this workshop for future broadcast. Now I'd like to introduce Guy Payne, who's the director of the Sustainable Energy Outreach Network.
Okay, thanks, Paul. Just quickly, the Sustainable Outreach Network is a nonprofit organization based right here in Brattleboro. And mainly what we are doing is creating an interrelated network of local businesses, educational institutions, and private sector folks to really improve the economic sustainability of this region. And we're not just talking Windham County. We're also talking the New Hampshire, Cheshire, Franklin County, Windsor, and all the neighboring counties. And mainly what we are doing is developing and promoting, or promoting and developing really promoting the development and commercialization of renewable energy and energy efficiency products, processes, services, and technologies. And what we do, the way we do it is unique in that we're really trying to form a network, an interrelated network of all businesses, so that we're functioning collaboratively together as opposed to independently. So that's the nature of what SEON is doing. But you're not here necessarily to hear about SEON as much. So what I would really like to do is introduce Peter Temple, who is a member of SEON, associate professor at Keene State in the architecture department, professional engineer, energy consultant, came up to this area. Well, you were up in this area, graduate at undergraduate work. But he's been involved with sustainable building and design and energy consulting for more than 30 years. Professional career started in 1978 with Total Environmental Action in Harrisville, New Hampshire. Associate professor of architecture at Keene State since 1991. And teaches courses on sustainable design, building science, energy efficient systems for high performance buildings, and renewable energy systems. We're really fortunate to have Peter as a member of SEON and certainly speaking tonight. Thank you. Peter, it's yours.
So I'm going to modify the introduction a little bit by, they refer to me as the keynote speaker. I guess I think of myself, I'm the first speaker here, the introductory speaker. And I get the fun part here. For what's fun for me is to try to help everybody. The title is Understanding Heat Pumps. And heat pumps often seem like a black box sort of magic thing that people don't really understand. And even worse, sometimes seem to defy the laws of physics. They kind of, it's like you get more than you put in. And that's not the way the world works. So I'm going to do one of the things I enjoy doing when I teach this subject, and I teach systems courses and so on at Keene State, is just try to give everybody a basic good gut feeling for how these things work. And then we'll go on and we'll crunch a few numbers just to see, how do you figure out, how much do you get from one of these heat pumps? What is it giving you in terms of energy, and how does that compare to other sources of energy? And then we'll get into costs. And I'm going to actually shrink this down and try to do this in a lot less than the 45 minutes and give more time to the fellows back in the room, to Joe and John and Chris, because they're the ones, the folks from who are here from Mitsubishi and Fujitsu are really it's those systems, those air-to-air heat pump systems with this new technology called VRF, variable refrigerant flow. They can really explain in great detail, answer a lot of the technical questions you have, And also, they have a history of lots and lots of installations and can talk to you about the problems people run into and so on. And we have some people, other people in the room, and Bert is also going to talk about that. So, and then there's two qualifying things I wanted to mention before we get started here. One is that I've got a few slides here just because you're supposed to have PowerPoint slides when you do this. I'm more comfortable, writing stuff out here on the board, and we'll crunch some numbers. But and the talk I have sort of outlined on these slides is all focused on really just the understanding the heat pump, like I said, and crunching some numbers. But I think we should step back before we do that with a couple sort of qualifying things. The talk makes it seem like this decision, or the decisions you make, whether or not to put in systems like this and so on, is just about cost. It's just about how much it costs per BTU or per kilowatt hour, however you want to figure it out. And I think we all know, most people assume, that there's a lot more at stake here than just saving money on your utility bill. What it's really about is saving the planet. We're really, and it's my belief, and what I talk to my students about, that this planet, we're now facing the greatest challenge we've ever faced. It's the greatest threat to this civilization as we've known it. And we know that one of the best ways we can address that is by reducing greenhouse gas emissions. And so what's real important is to use less and less fossil fuels. And one way to do that, doesn't follow directly. It takes a few other steps. But one way to reduce consumption of fossil fuels, in other words, just burning stuff in your building and sending the combustion gases up the chimney, is instead, if you can run your building on electricity, you at least have the potential then of getting that electricity from renewable sources, whether it's a PV array on your roof or a community PV array or some hydropower or whatever else, or just paying a little bit extra to the utility company to buy green electricity, and you can be instantly all green. So I think there's a lot to be said here about global climate change, and people make these kinds of decisions about heating systems for different reasons. For some people, it's just the out-of-pocket utility bill, and for some people, it's a combination of that and environmental concerns, and for some people, it's mostly the environment. So that's one qualifying I want to make. And sort of related to that is another thing that I'm not talking about at all in these slides, is just the subject of energy efficiency. So we're just going to focus tonight on the heating system and comparing like different systems to other systems. But if you're really trying to, both for your own personal self-interest, lower your heating bill, and if you also care about the environment, the most cost-effective thing you can do first is make your building a really good building, which means an energy-efficient building. So that means doing as much of an energy retrofit you can on an existing building, even approaching what we call now deep energy retrofits, which is making that building basically as good as a new building. And to give you a rough idea of where to set sort of the goalpost, where you can go, there are, I think, now about 40,000 buildings in the world that have been built to this energy efficiency standard represented by this German passive house model. And if you meet those standards, the amount of energy you would use for space heating your building compared to what we typically use for buildings around here would be about 1/10 as much. So a German passive house certified building uses roughly about 1/10 as much energy for space heating as a typical American building. So in other words, once you have that kind of building where really, the big chunk of energy you're paying, if it's a residence or families living there, it's really domestic hot water. And then you want to focus on how do I get my domestic hot water energy bill down, and then you want to think about lighting, and you want to think about plug loads. But space heating should almost be inconsequential if we do our buildings right. And we're used to space heating being this, we're paying people around here paying $5,000 to get through a winter for oil, right? And it should be almost nothing, okay, if we had really good buildings. So I wanted to talk about those two things up front. So now heat pumps. Most of you probably live in a building that has a refrigerator and a kitchen. And I want to just think about what a refrigerator does for a minute. And let's simplify a refrigerator. Let's say forget about the freezer compartment. Think of it as just a box where somehow we're maintaining the inside of that box at, we used to say 40, maybe it's more, supposed to be, I guess, 38 degrees Fahrenheit. We're going to maintain the inside of that box at 38 degrees Fahrenheit, and a refrigerator somehow does that, right? And all that goes into it is electricity. So it runs off electricity, and there's some kind of equipment in there, set of equipment, that takes heat out of the inside of that refrigerator and does what with it? Where does it go? That goes into your kitchen somehow. And if you feel around the outside of a refrigerator, you can find some place, or an older one, maybe there was some coils on the bottom or something, you can find a place that's warm. So there's a mechanism in your refrigerator that's continually, or as needed, removing heat from inside that refrigerator and dumping that heat into the kitchen. Okay? And of course, if it only had to do that once, if the refrigerator had perfect amount of insulation around it, R1000, and you never open the door, you could do that once and it would stay at 38 almost forever. But of course, what's happening all the time, since there isn't super good insulation around it, heat always flows from a higher temperature to a lower temperature. That's downhill for heat. Okay? And so even though you have this pretty well insulated, heat is gradually flowing, because your kitchen's, say, at 70 degrees Fahrenheit. So the air all around here is at 70. This is at 38. So gradually heat, there's no, let's make the box airtight. There's no air flowing back and forth here, but just heat by transmission. Heat is being conducted through the insulation. Conduction rate is inversely proportional to the resistance, the R value. So if you have twice as much R value here, the heat will leak back in, move back in at half the rate. But the heat's moving back in, and then as necessary, the refrigerator comes on and pushes that heat back outside, right? Any questions so far? We all know that's what refrigerators do, right? That's how they work. So how does it do that? How does it actually do that? Well, this was an invention in the early 1900s. It's called the vapor compression cycle. I think it's not that great a name. If I were naming it, I'd probably call it the evaporation condensation cycle or something like that. But what's really happening here is that you run an exotic liquid into your refrigerator, and that liquid changes from, that refrigerant changes from liquid state to gaseous state. It evaporates, which we call evaporation, right? So what you're doing is you evaporate that liquid inside here, and then you have you have to plug in your refrigerator, right? So you've got wires that are coming in, and you've got this unit operating here, which is electrically powered, and it's a compressor. It's basically a pump. And what it does is it takes that refrigerant, which comes in here, actually, in the liquid state. It absorbs heat to evaporate into the gaseous state. This pumps it out here and pumps it up to a higher pressure, which makes it really hot. So now you've got this really hot gas, and it comes out to this coil. And what these, this coil inside here represents, lots of linear feet to give you lots of surface area for good heat exchange, So you're absorbing heat from the air inside the refrigerator. You're coming out here, and then in your kitchen, which is somewhere now, it's on the outside of your refrigerator, right? That place where you can put your hand and it feels warm. What's happening is in this coil, enough heat is leaving so that that gas now condenses back into a liquid. And then it's still at pretty high pressure, so this expansion valve then lets us reduce that higher pressure to low pressure. So now we have a low pressure liquid going back in here. That liquid is absorbing heat. It's evaporating. It sort of absorbs, it picks up a lot of heat from inside here. We pump it back out here. It's pumped up to now it's a very hot gas. We condense it again here. And it just goes round and round. So it is a cycle, and it's an evaporation condensation cycle. And it takes outside energy to keep it going, and that's the electricity that runs the pump. Okay? Can you hear me okay in the back? Because I can talk louder. Okay. So that's how your refrigerator works. And if you think about it, what it's doing is it's actually picking up heat from a cold area and then dumping that heat into a warmer area, right? So it's taking that heat and it's running it in the opposite direction that heat wants to go, right? Naturally, heat's always flowing from a higher temperature to a lower, so it's going back the other way. So what we're really doing is moving that heat uphill. So that's why this, in fact, your refrigerator is a heat pump. So what we mean by a heat pump is it's a mechanism, in this case, a set of equipment that's carefully designed to run a certain way that picks up heat from one place by evaporation. And we call that, I won't get into the scientific detailed stuff too much tonight, but if you may remember something from a science class about latent heat of evaporation, which is another name for it when you're going the other way, is latent heat of condensation. Turns out there's a lot of substances can actually absorb a huge amount of heat without much of a change in temperature when they evaporate. And then you get all that heat back when it condenses. So it's a great way to pick up heat from one place and dump it to another. So your refrigerator is indeed just a heat pump. And it's this vapor compression cycle, or maybe we should call it the vapor evaporation compression condensation cycle. That's what it does, is it pumps heat uphill. Does anybody have a question? Yeah. What that's about is this side over here is kind of from my arm to the right. That's the high pressure side, and this is the lower pressure side. And so we've pumped it up to a high pressure, and so that high pressure doesn't get all the way back over here. What this is a valve is that it meters, basically lets the refrigerant back through at a lower rate and without transferring that pressure. Now, like I said, qualifier I said at the beginning is when we get into super technical details, I'm going to defer to one of the guys in the back of the room. Joe is an engineer at Mitsubishi, and I'm sure he can get into a lot of technical stuff later. But this is the basic concept for how a refrigerator works. And so actually the electricity we're using is just to run this cycle. And I was talking to some people at SEON not too long ago about this. Actually, somebody from the audience had a really good model. They said, you mean it's sort of like you're using the electricity to run a conveyor belt. And the conveyor belt could be one of those things that, like, putting bales of hay up into the hayloft in the barn or something. We're going uphill, and we're transferring stuff from one place to another. We're not converting the electricity directly into heat at all. So this is quite different. A lot of you are used to the idea of maybe, you know about electric heat, electric resistance heat. It's always been too expensive for most people to use. It was inexpensive to install. I used to teach my students 15 or 20 years ago that electric resistance heat made no sense at all. It was easy to show them by calculations that it was 4 times as expensive as oil. Now it's only about 25% more expensive than oil. But it's still, electric resistance heat is still not something you would intend to. Electric resistance heat takes electricity and converts it directly to heat. This isn't doing that at all. This is using electricity to run a compressor that's keeping the cycle going, pumping it around, and pumping this up to a higher temperature. And so the electricity is like the motor running the conveyor belt. And what the conveyor belt is doing in this case is taking heat from one place and delivering it to another place that happens to be uphill in temperature, lower temperature to higher temperature. Yes?
Okay, I'm confused.
Okay. This whole thing is full of this refrigerant fluid. There's no air in there at all. So it's just pumping that around. But I'm saying, you're right. I mean, what's happening here is we're moving refrigerant around, right? And we're pumping it up to a higher temperature and pressure and then dumping that excess heat out here. And so letting it get quite a bit cooler and down to the liquid state to go back in. So I'm saying it's analogous. If you think of this entire unit, of course, you need the whole thing operates together, the 2 coils and the compressor together, evaporating on one side, condensing on the other side. But it operates effectively as if it were a pump. So that's what we call it, in quotes, a pump. This vapor compression cycle, what it does is allow you to absorb heat from even a colder place and then reject that heat into a warmer place. Okay? So now you know how that thing in your kitchen works, right? That's a heat pump. So everybody here is, well, some of you may not have refrigerators, or my mother always called it the ice box because she grew up with just using ice. But you know, a lot of you have refrigerators, and that's what it is. So you have a heat pump in your kitchen if you have an electric refrigerator. Yeah.
So if I'm understanding you correctly, this would be different from just a simple heat exchanger in that you're taking advantage of the phase change from liquid to gas?
Exactly. And a heat exchanger just means something where that, and typically it has a lot of surface area, where we're trying to exchange heat from one medium, a hotter medium, to a cooler medium. So the car radiator is a heat exchanger. You're trying to get heat out of the hot coolant, the hot antifreeze that's running through. We're trying to get that out to the air.
Solar hot water.
And, yeah, so, and we actually, these two are heat exchangers. I mean, what this coil is doing is absorbing heat from the air that's in there. And so that is a heat exchanger that's picking up heat from air, the air inside the box, and putting that heat into the refrigerant. And this is a heat exchanger that's taking heat out of the refrigerant and releasing it, rejecting it into the room. Okay?
Right. But the change from liquid to gas and back.
That's what helps make this a really powerful thing. That's the key to this. The key to this is phase change. It's liquid to gas here, evaporating from liquid to gas, condensing from gas to liquid. That's what makes it work. Yes?
I think this is related. I don't understand for a refrigerator why you need to compress it. Why doesn't it just go out and then the heat goes away, goes into the air?
Well, you have to keep it moving, so you have to have a pump anyway, right? A pump to keep it moving. And so you would at least need a pump to do that. And it makes it work more efficiently if you can. And what you really need to do, you're going to reject the heat into a hotter environment. You know, it's 70 degrees in here. It was only 38 in here. So if you can run the compressor, what you do is by compressing it, when you take a gas and squeeze it down, it raises the temperature a lot. And so what you're doing is getting this up to a higher temperature, so now it's warmer. Remember, that refrigerator feels warm to your hand, so it's actually warmer than 70 degrees Fahrenheit. And in order to reject that heat into the room, you've got to have it pumped up to that higher temperature. So that's what the compressor does. Okay? So let's move on here a little bit. So normally when we talk about how efficient some system is, like your oil burner, you know, if you've got a lot of people here probably have an oil-fired furnace or an oil-fired boiler that makes hot water for your hydronic heating system or something. If we talk about burning some fuel to get heat out of it, to get energy, usually we talk about efficiency this way. It's how much we get out of it divided by how much we put in. You know? So if, say, on a burning oil, a gallon of oil contains about 138,000 BTUs. You may see some references say 140. But if you have 138,000 BTUs in a gallon of oil, and when you burn that on a seasonal basis, if you're only operating, even though when they check your oil burner and they say, you know, you get the little tag, if somebody measures the efficiency by looking at the carbon dioxide content, they say it's 82% efficient or something. On a seasonal basis, probably what's more realistic is 75% efficient. So 75 or 73% of 138,000 is only 100,000, right? So if you got 100,000 BTUs out of each gallon, divided by 138,000 in each gallon, then the efficiency would be 0.73, right? So it's always going to be some number less than 1, right? We never get as much out as we put in because you never get all complete combustion. You know, so there's some unburned particles. You can see smoke going up the chimney, so clearly you didn't burn everything. With oil, you know. Natural gas is going to be a little better, a little cleaner burning, so the efficiency is going to be a little higher. But generally, with anything, when you talk about efficiency, efficiency is always a number between 0 and 1. You'd like to get it really close to 1, but you're never going to quite get there because there's always going to be some waste heat, whether it's cycling, the system shuts on and off. Every time it shuts off, the excess heat, a lot of it goes up the chimney, or incomplete combustion, things like that, right? So I think we're used to that concept of efficiency. What's the efficiency of electric resistance heating? Anybody? all the electric companies say 100%, right? And the truth is, if you meter the electricity as it's come through the wall into your building, if all that electricity gets converted into heat, which it usually does, then it is 100%. However, of course, if you look back at where that came from in the power plant and the amount of fuel they had to burn at the power plant to eventually get that much electricity to come into your building, it ends up to be more like about 30% efficient. Pardon? 30, yeah. About 2/3 of it was wasted. Well, it's used to heat up the atmosphere, help accelerate global climate change. So anyway, somebody talks about 100% efficiency. That means, well, you've got electric resistance heat. If you just measure it by the electricity that's already come into your building, then all that gets converted to heat. Yeah, then that could be 1. So that would be an efficiency of 1. But most anything we burn, wood stoves. I guess it's all over the place. There's modern. Somebody here may be experts in wood heating. There's a lot of new technology, but I think the old-fashioned, like basic wood stove, probably about 50% efficient, right? Something like that. Okay, well, heat pumps are different. So heat pumps, we don't talk about efficiency. We talk about coefficient of performance, or COP. Sorry about the shift here, but what this is a fraction where the denominator is the operating energy, how much electricity our compressor is using to run that vapor compression cycle. And the numerator in this fraction is just how much heat we moved on our conveyor belt from one place to the other. And it turns out we can actually move a lot more heat from point A to point B. We can move more energy in the form of heat than it takes to run that pump. It's not magic. We're not creating something from nothing. We're not creating more energy than we had. We're just using our energy differently. We're using our energy to run a pump, and that pump is moving heat. It's not making heat. It's picking up heat from one place and rejecting it in another place. So if you look at heat pumps, people will talk about COPs of larger numbers, like 3, 4, 5, depending on, and COPs can be all over the place depending on operating conditions. Of course, it's a lot easier to run. A heat pump will transfer a lot more heat if you don't have to go quite as far uphill. And if you're starting off at a warmer temperature, it'll work better. So the COPs don't necessarily mean a lot unless you know exactly the condition for which it was defined. So I guess that's what my next slide here said. So you'll see COPs 3, 4, 5. What does that really mean? So what I want to talk about here, one thing that I think is meaningful is the seasonal COP. What do I mean by that? I mean, if we had a system installed in a building and we ran it for an entire heating system, from October to April or whatever you consider your heating season. We ran it for that entire season, and we measured all the electricity that heat pump used. And we know somehow, that's the hard part, how much heat that building produced. Now, people have actually done some studies. There's a lot of models and predictions, and you can do calculations and predict what things will use. But what I like to do is rely on actual performance. And so I know of some studies that other people have done and presented at conferences, and I guess you sort of believe that stuff until you see otherwise. But I know of an actual building not far from here in Keene. There's a company that's done a lot of work in New England, mostly on commercial buildings, a little bit of residential, but mostly commercial. Kohler & Lewis Engineering was was the first real mechanical engineering firm to do a lot with air source heat pumps in this area. And so a lot of you over here may be familiar with the Putney School. There's the new field house at the Putney School. That must have been like 5 years ago or so, 5 or 6 years ago, maybe even more. And that entire building is heated with air source heat pumps. And Kohler & Lewis Engineering, one of the first things they did was install these systems in their own building. Their own building is just an old VFW building in Keene, not very well insulated, just kind of a clunky old building, but a nice compact shape, efficient size and shape. And they knew very well how much, They knew from an operating point of view, from actual measurements, how much heat their building used, because they'd occupied it for many years. And they had an oil heating system, and they kept track of how much oil they used. And they kept track of the degree days. Anybody can go, it's easy to find out how many degree days you've had in the local area. Like the oil companies keep track of that and so on. So then they installed an air source heat pump system, and they kept careful track of how much electricity they used to go through the entire heating system, the heating season. And they also kept track of the degree days, how cold it was that, because one year to the next can vary quite a bit in cold. So you kind of like to normalize everything by looking at degree days. And what they found, they've gone through 5 entire heating systems now. They're starting their 6th winter heating that building solely with air source heat pumps. They left the oil system in case they ever needed to use it, because this was all 5 or 6 years ago. This was all pretty new around here. And what they found is that, and we can get a more exact and up-to-date number maybe from Adam Kohler, but I think they're finding more around 2.4, 2.2 to 2.4 for seasonal COP. I sometimes, to be really conservative on the safe side, use 2. And I was talking to, Joe may have some updated numbers. Earlier I was talking to Joe Fowler from Mitsubishi, and he was saying that some studies, one study he's seen, not too many people have done large studies on this, he thinks a more realistic number might be between 2.5 and 3, and I think that's very believable. One thing I should say that I didn't include in the slides, and should mention, is that you may still find people out there who say, a heat pump, an air source heat pump, that could never work in this climate. We had the building I'm in at Keene State College, we have this brand new building, and it's all done with air source heat pumps. It was a tremendous battle to make that happen, as one of my colleagues here knows. And one of the things, when we were interviewing big architecture firms, the college wanted to have somebody from Boston or New York, some big architecture firm, because we all know it's the people from the big cities that know what they're doing, right? I believe it's really the opposite. The big firms don't have any motivation. They don't go to conferences. They don't know what's happening in the field because they don't need to. They have nice websites. They dress nicely. They would be here with a coat and tie tonight. And so they get lots of repeat business just by doing things the same way they did 20 and 30 years ago. So we interviewed this large architecture firm from New York City. It was so big they even had their own in-house engineering firm. They had a 40-person engineering firm. And the head of that engineering department within the firm came up, and he was doing they were doing their dog and pony show about why we should choose them to design our new building. And we said we wanted a super sustainable building. And he said, well, if you want a sustainable building, these are some things you could do. You could do ground source heat pumps, and you could maybe do, some of the architects we talked to wanted to put a wind turbine on top of the building. This is down in the Valley of Keene. It's amazing how out of touch some people are. And then he made the comment, he said, well, you could never do air source heat pumps. They would never work up here. This is the head of a big New York engineering firm. Also, Kohler and Lewis Engineering recently did a large medical building in Keene, 4 or 5 story building, and they did the heating system. They were doing the heating system for the whole building. And they, of course, were doing air source heat pumps. They'd already done lots of buildings by now. They did a big office building in Portsmouth, and they've done lots of different buildings, all with air source heat pumps. But there was, I think, on one of the floors of the building, there was this sort of high-end medical, this doctor's office, and they decided they didn't really want a local Keene firm, doing their part of the building. So they got this outside Boston architect to come in and do their whole floor, and they also wanted a big engineering firm from Boston to do the HVAC system for just that floor. And of course, that means they have to tie it into the rest of the building. So this engineering firm called up Kohler and Lewis and said, well, we want to know how you're doing the rest of the building because we're going to do this one floor, like the 3rd floor or whatever it was. And we want to tie a system in. And Kohler and Lewis said, well, we're doing air source heat pumps. The next thing, there was this mass email that went out to all the people working on the job and the architects and said what are these country hick engineers up in Keene, New Hampshire think they're doing, putting an air source heat pump system in this building? Don't they know that air source heat pumps can never work like north of Virginia? Joe, of course, didn't even respond. And later on, it turns out they put in air source heat pumps on that floor, too. So I guess they eventually figured it out. But what you will find out is that there's this because it used to be true before the new technology we have. This is VRF, variable refrigerant flow, and the guys from Fujitsu and Mitsubishi can tell you more about this. But it's a whole new technology that was developed in Japan. Turns out they've been doing it for 20 years. They've been heating and cooling their buildings over there with these air source heat pumps. And 90-some% of all new buildings of any size, skyscrapers, everything in China and Japan are done with these VRF air source heat pumps. But the types it's a very new technology. They have these inverter-driven modulated compressors that can vary in how much output they have. And they, there's a lot of design features they did. It's basically like a new piece of equipment. So you may encounter more traditional, people out in the field, installers of heating and cooling equipment, and mechanical engineers, and even people, especially people at big firms, that think, wait a minute, heat pumps can work well in North Carolina and South Carolina and Virginia and places where it doesn't really get below freezing much. Because the old types of heat pumps, air source heat pumps that used to be used, the efficiency drops way, way off when you get down below 40 degrees Fahrenheit. You get down near freezing, and they basically convert over to run electric resistance. So this technology we have now, these VRF air source heat pumps, or technology they have, is just a huge breakthrough. And I can't think of anything else that's happened in the HVAC industry, the heating and cooling industry, in the last 30 or 40 years, or even longer, that's been as dramatic a shift as this. This is like a huge breakthrough that I think is changing everything for lots of people. Okay. Maybe I will use the 45 minutes. So what does it mean in terms of cost? And notice that I'm using, this is a COP number of 2.2. So these are just rough numbers. You should maybe put in 2.5 or try 3. But anyway, one way to figure this out, so this thing's going to run off of electricity, and I don't know what you're paying for electricity. I think where I am in New Hampshire, it's around 16 cents a kilowatt hour. If you add everything up, total it, Vermont's, some of you, it's probably like that. You could put in 14 cents if that's what you're paying, or 15 or 18. But put some number in there for how much you're paying per kilowatt hour for electricity. And this is, of course, all residential numbers. If you've got a big outfit, I think, big buildings around here, Keene State stuff, they pay 10 cents a kilowatt hour. But if you've got, residential level, 16 cents a kilowatt hour, and just take that number and divide it by the COP. It's like, so if for every kilowatt hour you used, you're actually, to run your heat pump system, you're actually transferring 2, then we would just divide by 2, and it'd be like getting electric resistance heat at 8 cents a kilowatt hour. If it's 2.2, I shouldn't have dropped off the other figure here, but I think this is, it comes out, it's about 7.5 cents a kilowatt hour. So that's an easy, quick way to figure out what the energy is costing with this. If it was really a COP of 3, then you're down almost to 5 cents a kilowatt hour. Okay? And then what can you do with that? Because a kilowatt hour, we're used to using that for electricity, but it's hard to relate that to heat, how much heat costs. Well, it turns out that a gallon of oil, and of course I'm talking seasonally now. Like I said, a gallon of oil actually contains, if you could burn it all completely, 138,000 BTUs. But in reality, you can't, and on a seasonal basis, you get maybe 100,000 BTUs out of it. Well, 100,000 BTUs is about 30 kilowatt hours. Nice round number. It's actually 29.3, and but if you want to keep a number in your head, just use 30. There should actually be parentheses here and here. There's a little typo here. But if you take 30 kilowatt hours in 1 gallon of oil and multiply that by, say, 7, and it actually should be 7.4, that got dropped off. Otherwise, this would be 210. If it's really 7, this would be 210. But we're talking about, so what this tells you is heating with an electric supplied air source heat pump, if you had a COP even of only about 2.2, and you're paying 16 cents a kilowatt hour, that's like paying, 210 or 220 for a gallon of oil. How many people are paying that little for oil? Okay, so that's why it makes sense if your only option is oil. Now, people have other options, and what some of them are. By the way, there's a lingo, part of the lingo here in the field in engineering. It's 100,000 BTUs as a therm. A BTU is the amount of energy. How's a BTU defined? Does anybody know? It's the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. It's also 1 BTU is about how much energy you get off of lighting 1 wooden match. So if you light 100,000 wooden matches, 100,000 is a big number, you would get about as much heat as you can on a seasonal basis by burning a gallon of oil. A gallon of propane, propane is more efficient in combustion, but a gallon of propane only starts off with about 92,000 BTUs. So even if you burn it at a higher efficiency, I forget what number I used there, but I just tossed in a number, a higher efficiency than you would for oil, you still only have about 0.8 of a therm, or 80,000 BTUs. But 100 cubic feet of natural gas, that's just about a therm. That's 100,000 BTUs. A quart of wood is a lot of, these are very rough numbers here. Depending on what type of wood you have, how dry it is, you see numbers ranging from 30 million BTUs down to 25 million. Is that right, Eli? That should be your area. Okay. But then if you figure, you say you had 25 million or 25 or 24, I try to be on the conservative side, and you 50% efficiency, you'd have to take half of that, on a seasonal basis, 50% efficiency. So that would be about 120 therms from a quart of wood. So just to give you some idea of how these things compare, I put question marks everywhere because prices can vary all over the place. I don't know what you might be paying for oil now, maybe $3.60 a gallon. So if you're paying $3.60 a gallon, you're paying $3.60 a therm. Propane, I was just talking to a friend the other day. If you own your own tank and you can get the propane companies to bid against each other, I have a friend who just and heats his house with propane, and he got a delivery, I think, what did he say, $2.10 a gallon. So $2.10 a gallon would be around, $2.50 a therm. So big commercial users can get low prices. You can also, if you're a really small user and just use it for cooking, you might be paying $4.80 a gallon. So propane prices vary all over the place. But you can, that's easy to figure out, 92,000 BTUs a gallon. Natural gas, we don't have access to it around here. We're not on a pipeline. But if you're in a city, it's like down around $1 for 100 cubic feet. So that's $1 for a therm. So that's, if all you care about is cost, and you're not worried all about fracking or environmental consequences or anything, and you had access to natural gas, that's a no-brainer. There's nothing else that comes close to natural gas. Of course, if you want to reduce your carbon footprint and you don't want to burn fossil fuels and you don't want to hurt the air, then maybe you're not going to do that. Wood, if you take the number I had on the previous slide and convert that, that's about $1.67 per therm. Electric resistance is just, if you had a COP of 1, in other words, it's just saying, okay, what's 16 cents a kilowatt hour? 16 times 30 is 480. So that's like paying 480 a gallon for oil if you used electric resistance heat. And the air source heat pump at the bottom here is maybe 210 or 218. If, like with Joe's number of maybe instead of 2.2 COP, 2.5 or 3, that could be a much better deal and come down actually less than wood. So I'd see actually, depending on what you're doing with wood and whether you're buying pellets and how efficient your stove is, and depending on what your COP actually comes out with air source heat pumps, I think often those two end up in the same ballpark. So this number, this 218 at the bottom, that's probably a little higher than it should be based upon maybe latest information. And I think, so we did that. What else was I going to say? So that's kind of what I had to say about this stuff. And my next slide was just questions. And I don't know how I've kind of used my time, haven't I? Most.
Yeah.
Okay. Any questions? You want to go back to that at all? Yeah.
So it's drawing heat from the outdoors?
Pardon?
It's drawing heat.
Oh, yeah. I never made that point. Sorry. That was, I didn't want to use too much time, but so one way to think of the heat pump, take your refrigerator. We went way back to that first slide. Take your refrigerator, take off the door. Okay, so there's no door on your refrigerator. Then move the refrigerator over. Have your kitchen has a door to the outdoors, and say it's 40 degrees outside, shove your refrigerator into the doorway so it blocks the doorway. Now your refrigerator is trying to cool down the inside of the refrigerator to 38, but it's 40 degrees outside. It can never make it, so it's going to run and keep extracting heat, absorbing heat from the great outdoors, from the atmosphere, and it's going to be dumping that heat into your house. And then what you can do with a heat pump is actually you can reverse the cycle in the summertime, and what was the evaporator coil becomes the condenser coil. What was the condenser becomes the evaporator. So in the summer you run it the other way and cool your house. And that beats pulling the refrigerator out, turning it around the other way. So yeah, what the heat pump does is extracts heat from the outdoor atmosphere, which is nice in a way because the atmosphere is moving around and you have source of more air. And these things the one at Kohler and Lewis, they've gone down to 18 degrees below zero, minus 18 Fahrenheit, and the thing is still performed enough. I mean, the performance curves drop off. I think the Mitsubishi Hyperheat, I'm familiar with that performance curve. I think it's still at 100% effectiveness down to 5 degrees above 0 Fahrenheit. And at 0 Fahrenheit, it's like 95%, and then the curve starts to drop down a little bit after that. So they definitely, getting down 10 below 0, 15 below 0, effectiveness becomes not so good. But we don't have a lot of hours at those temperatures in the winter. Pardon?
I had 4 days.
4 days at those two. But if you go down to 20 below 0, it's usually between midnight and 5 in the morning or 6 in the morning, and usually by 10 in the morning it's back up close to 0 again. I mean, there's no problem operating at 0 or 5 below 0 or 10. So if usually it's a short time down at those. Now, another related question, besides pulling heat out of the outdoor air, you might ask about, well, why not ground source heat pumps? And it seems on the face of it that ground source heat pumps would make a lot more sense, right? Because in the winter, when the air gets really cold, the ground's supposed to be still at 45 or 50 degrees. So why not, pump water through the ground or extract water out of the ground that's at that nice 45 or 50 degrees, and why not take that heat out of the water? And now with the water's cooled down, then you dump that cooler water back in the ground and hope the ground's going to warm it up again, right? Well, it turns out, first, those systems are really expensive. Instead of spending maybe $5,000 or $10,000 on a system with an air source heat pump, or maybe it's less, and those guys will fill you in on that, now you're going to be spending $30,000 to $40,000 because you've got all that site work. You've either got big borehole wells, or you're trying to, I don't know if people try to do this much anymore, but people, dig big shallow trenches and have hundreds of linear feet of pipe. You have a complex system. You have to have site work people and plumbers and electricians. And it turns out that some people have been having problems with those systems working well because over time, you're actually cooling the ground down all through the winter more and more. And eventually, your water starts to get down to freezing, and people have to put antifreeze in the loop. And so, it may be an okay system if you're in middle latitudes of the U.S. where your cooling season and heating season are balanced, and you're kind of cooling the ground down all winter, and by the end of the winter you've cooled it down a lot. But then summer comes, and now you're doing heat the other way. You're extracting heat from your building and dumping it in the ground, and you're warming the ground back up so that by fall you can go the other way. But still, I mean, most people are not doing those systems at all because they're just so incredibly expensive. Oh, and the performance benefit is only slight. So people have studied lots and lots of buildings on a seasonal basis where they've done ground source heat pumps versus air source. And one study I've seen, which may be a little out of date, when I was talking to Joe, but it said that looking at 125 buildings, and I don't remember how many of each one, ground source and air source, over the whole season, the average COP on the ground source was 2.6, and the average COP for the air source was 2.4. So less than a 10% difference in performance, but an enormous extra cost. I mean, maybe 10% slightly more efficient with the ground source, but at an enormous cost. So people aren't doing that. Yeah, there's a lot of people are thinking about a lot of things like that. So yeah, on the one hand, you could say, hey, if I could make a little microclimate around that outdoor unit and warm things up, that could work a lot better. Maybe a greenhouse, stuff like that. But remember, you've got to constantly have new air coming in. If you just had one closed-off room around it, you're going to cool that room down dramatically, really fast, to extract heat from it and pump it into the building. I bet these guys from Mitsubishi and Fujitsu can talk to that better than I can. Yeah.
My understanding is that these are recommended primarily where you have some other primary heat source in most places, because there's a point at which they become too inefficient. But is that, will they function whatever the temperature is outside? Or what happens at that point?
You hear that a lot. I hear that a lot. I basically completely disagree with it, because I would say, but I think there's some subtle ways in which there are some things to think about, you know. So on the one hand, if people can do huge buildings, large buildings with air source heat pumps, then you ought to be able to do a small but terribly insulated, leaky house, right? I mean, it would be a stupid thing to do. You should always make your building it's much more cost effective to make the building as energy efficient as possible before putting in the system. But it's not like there's something not good about them. They can't meet the load. Now, we are in the marginal. I mean, that's why, you know, when Kohler and Lewis put in their system, they left the oil system in there because they didn't know. You know, nobody else had had gone through a winter with any of these things around here. So they left it in. Have they ever had to turn it on? No. Down to 18 degrees below zero, it's been fine. And so some of the first big commercial installations they did an engineering office building over in Portsmouth. And they talk to the client. They say, look, you know, we think this will work fine, but if you want to be perfectly safe, if you want to make sure in those nights, if you goes down to 20 below zero at night, and you want at 8 o'clock in the morning when people come in and it's still, you know, 8 degrees below zero outside, you want make sure you get tons of, we'll put in some backup system. We'll put in something cheap, a little electric resistance heating in there in the units to beat it up. So they did that quite a few years ago. The company, they've never had to turn it on. It's never been used. Okay, so people with a lot of experience with this talk to the client, and maybe sometimes the client wants the backup heat. Now, other companies that are not very experienced with it, like the engineering company that did the building I'm in at Keene State, they were very worried about this, and they wanted to be sure that they could always deliver warm enough air in the winter and cool enough air in the summer, and so they put in all kinds of backup systems. So what we're talking about here is an outdoor unit and an indoor unit, and you've all seen this kind of thing with just air conditioning type units, right? And the outdoor unit there's a coil, and you're extracting heat, picking up heat in the wintertime from that colder outdoor environment, and you're running in just refrigerant tubing, so you're not circulating any air between indoors or outdoors. The only thing that's going back and forth between outside and inside is the refrigerant. You bring that refrigerant inside, and they have a number of different types of units which they'll talk about. You can get wall-mounted units, you can get ceiling cassette units, you can get floor units, or that sit on the floor. And all those units do is bring in room air and heat it as necessary and send it right back to the same room. So if you have a ventilation system for fresh air, that would totally be separate from this system. All these systems do is they take room air and heat it or cool it and deliver it back. Now you can get into more complicated stuff. We have in big commercial buildings, they have these branch controller units where you can actually, if you have a bigger building and you've got the sun on one side, and then people are kind of too cold on the north side and people are too hot on the south, you can actually pick up heat from one part of the building and deliver it to the other very efficiently. So you can do other things like that.
So what you're saying is it's a room by room exchange?
You can do lots of different things. You can have, if you have, again, they can probably tell you more, if you have a super insulated, like German passive house building, you might end up with just one point source. You end up with one terminal unit inside the building that's heating the whole building. And so because after all, a German passive house, you can almost heat with one electric hairdryer, right? So then if you have a bigger building or a not quite so well insulated building, then you might need a few more terminal units. If you go over to the Putney School gym, right, you'll see along the north wall of the gym there, I can't remember if it's 4 or 6 units about this big mounted high up on the wall that handle that whole gymnasium area.
Felix.
Okay.
Okay, I'm on. So I represent the non-expert part of the show tonight, and the consumer, let's say, angle on this. And I'll have a very brief statement about what we have done in our single-family residence as a reality check, perhaps, to all the other things that are being said today. At any rate, so a few years ago, my wife Harriet and I decided to build a energy-efficient net zero house in Putney, and we did. And we employed an architect, Bill McClay, who is the architect of the Putney School gym, by the way, which is a net zero building as well, using the air source heat pumps. But it's one of the first large gymnasiums done as a net zero building. So we had him design our house for us, and had Jonathan Klein, a local builder, do the building here for us. It was completed, and we moved in about 2 years ago, so we've had 2 years' experience in the house. But let me just tell you what it's like. It's net zero, and it relies on passive solar, a great deal of passive solar. We have triple pane windows, a very nice site which has a very good east and south exposure. And we have an array of solar panels, PVs, that are a 7.5 kilowatt system in the field away from our house, and a solar hot water collector on the roof. There are no fossil fuels in the house. It is all electric because it all runs from the solar electricity. We are not off the grid, however, and net zero meaning that we are producing as much as we are consuming. It's not that we don't need electricity in the winter. We do use electricity in the winter from the power company, but we do make it up and provide more in the summer than we need, so that the effect over the year is the net zero. So the heating system, more to the point today, is the heating system. Well, first of all, let me just say a net zero house, it's not a German passive solar house, but it's quite tight. And the R on the ceiling is about 65 to 70. The walls are about R40. Triple pane windows are 5 or 6, I think. So it's pretty tight, and it has to have an air exchanger to get air in because it's so tight. And that's a separate ducting system than the heating system. Our system, somebody asked before about how does it work inside the house. We have 2 units. One provides heat to the large open area, which is a living room, dining room, kitchen area, and that is forced hot air through a unit in the basement, still from the heat pump, but that part of the house is heated in that way with ducting and forced hot air. The rest of the house, the bedrooms and the downstairs basement areas, which do have solar gain because the house is on a hill, so the basement has also some solar gain. But at any rate, they are served by individual wall units from a second air source heat pump. Both the air source heat pumps are they're about 1 foot by 3 foot by about 4 foot, and they are in the back of our house near our bedroom. I was surprised. Actually, one of the funny things is when I first heard it go on, I thought I was in a city bus. It sounded kind of like a city bus. It was taking off like that. But it's not all that noisy, but it does go off and on intermittently. It's not always continuously making noise. It's not all that noisy, though, I don't think. Anyway, so that's our system. The air intake is from the for the circulation is in the cooler, unheated basement, which proved to be a difficulty in one of the quirks in our particular house. And I'll mention that perhaps again later. But that's the system that we have. It's a Daikin as the manufacturer. I didn't hear anybody from Daikin here, but that's what was chosen. And I don't know what these numbers of the seasonal efficiency ratio is or the seasonal performance factors are, but here's what came on the unit. And these are compared, you've all seen these kind of guides on all the appliances and all. They give you a range of what other products are in the same comparable products and how efficient they are. And this is This one is a little less than 50% compared to others, for your information. Okay. We've been in the house 2 years. We've only had a couple of days that were below zero in those 2 years. We do have a backup wood stove that we like wood heat, and we use wood heat mostly in the evening. So basically, the only time the heater is on most days is in the morning. So from 6 till 8 or 9 is the only time we use the heating at all, because on any day that has any sun, we get so much passive solar we don't even need any heat of any source. In fact, sometimes days like today it can get too hot in the house. Okay, so I don't know how it works below zero. It seemed to work the 1 or 2 nights we had it. I don't know how efficient it was, but it wasn't a problem. Okay, the quirks or tweaks we had to have on our units. One other thing is they're, at least to me, and I'm not a really handy guy, so programming it, getting to figure out how to set it up was baffling. It's so complicated. The controls, the internal controls that are available for you, is so complicated. I beat my head on the wall several times trying to figure out how to get it to go. And in fact, when we had to have one thing tweaked, somebody had to come from Rutland or someplace far away to get to figure out how to program the thing. So that was one of the annoyances that we had. Cold air. Okay. There's also a complicating factor of if you have a control in the front of the house for the big rooms, and you have individual room controls for each individual unit that you have in each room on the wall, like in our house we have 2 different, then you get to a master and a slave unit, and trying to figure out how to program all those things was another thing that was really difficult for us. Okay, so as my son says, how's it going? That's what he always says. How's it going? Well, we have a new house, so we can't compare what our heating bill is now with what it was in our old house. I mean, and we have nothing to compare it to. This is a new installation, so I can't tell you how much it costs. I can't even tell you how much it costs to put in, to tell you the truth. I don't even know what the unit cost was to put it in. All I know is we're not paying anything for heat, electricity, or anything in our house. In fact, we're making money because it's a net zero house, and in fact, I have tracked that, and we have come out almost right on the money for producing as much as we consume. This last year, we may come out slightly ahead, but because Green Mountain Power will pay you more for electricity than they charge you for electricity, you come out financially ahead. So we've gotten about, what is it, $500–600, something like that, back from them so far.
Can you share with us what your kilowatt usage was for your home and without the PV production, or those?
I mean, this is a new house, and
you know what the
yeah.
numbers are as far as total kilowatt usage?
Yeah, 9,000 kilowatt hours per year.
And is that net?
That's the yeah.
That's the gross number, and then you produce.
That's what same thing. Yeah. I mean, I just did the numbers for this past 12 months, and we were about 150 kilowatts ahead. We produced 150 more than we used.
So if you didn't have the PV system, you would consume 9,000 kilowatts. You'd have to buy 9,000 kilowatts.
Yeah. I mean, it was hot water too, but
How
yeah.
many square feet is the house?
Well, we think it's about 2,400, but somehow on the Efficiency Vermont thing I read the other day, it says 3,000. But I guess they're including all the basement storage spaces, and I don't know I don't know how they got the 3,000. We think it's 23 or 24.
Any idea how many of those kilowatts actually go into running the pump, the heat pumps?
All I can, no, I don't know how. I can't separate out how much is used for the heat pump. It's just that I think most energy people, and we had an energy audit beforehand, the architect goes over with you how much energy you're going to use, what temperature you like your room, how many baths per week you take. I mean, all the details about how much energy you're likely to consume in order to build you a net zero house. They really want to know how much you're consuming, right? And so, in fact, how many times a week did you want to build a wood fire, a wood stove? Fire had to be included in that calculation too, in order to size the PV system correctly. And all I can tell you is that the heating costs are by far the greatest cost use of electricity in the house, way higher than anything else. I wouldn't venture to say 2/3 or 3/4. I don't even know, but it's really high. It's the majority.
Question: how big is your array? Is the size? How many kilowatts is your array?
Is my what?
Your PV
Is 7.5.
7.5.
I thought I read something in the paper not too long ago about Green Mountain Power wanting to charge more in this net metering scheme because too many people were getting involved in it, and it was costing them more than they thought. Yeah. Do you know anything about that?
I don't know. I know that there are in other states. There's been serious complaining of power companies as people go. They lose their customer base that way, basically. I don't think Green Mountain Power has had quite that much. You want to answer?
I'm from Green Mountain Power.
There we go.
We're totally for solar and for heat pumps, so we don't have any issues. We're not proposing to charge more for solar installations. We're behind it, so it must be
okay. Am I mistaken in that? It must have been.
Yeah. Okay. All right. Thank you.
Kirk, it's good you were here.
Okay, what I'm going to do, I just need to move on.
Oh, I forgot the mice. The mice love those units, by the way. They really love them. One of the biggest problems.
Joe or John?
Guy, thank you for the opportunity to say a few words here. I'm just going to spend 10 minutes just talking a little bit about the products that are available and the different ways in which they're being used. So first slide here, the typical one-to-one. When we say one-to-one, one outdoor unit paired with one indoor unit, these are typically used to displace your fossil fuel. So say you already have an oil or propane boiler, and you're basically looking to reduce your usage by as much as possible by using one of these, much as you would use a pellet stove or a wood stove, something like that. You just get one system, you put it in your family area, and you set your conventional fossil fuel system to a much lower temperature. These come in a variety of ranges of BTU values, 9,000 BTUs being the smallest, up to about 36,000 BTUs in size. They come in a few different varieties, cooling only, heat pump, and then the one that we'll talk about just basically for the purposes of today is we call it hyperheat. The different manufacturers have different names for it. Basically, lots of heat at very cold temperatures. Most manufacturers have a product like that. The other option, or what you see, the other way in which these products are being used are as a whole home solution. Then you have an outdoor unit, and you may have up to 8 indoor units off of that one outdoor unit. This is really when people have the idea where they really want cooling and they only have some sort of fossil fuel for heating, and they don't have cooling in their home, or they're just trying to displace heating throughout their entire home. So again, this would just now be one outdoor unit, many indoor units connected to it. Each indoor unit gives you a thermostat. So you get one control point per indoor unit. So if you have 4 bedrooms, maybe you get an outdoor unit with 5 indoor units on it. One in the living room, one in each bedroom, that sort of thing. That would be your whole home solution. To give you a feel for the market, it's approximately 70-30 right now. 70% of the product is going to the one-to-one single units, and about 30% of the product is currently these multi-zone type systems. The one caveat right now is that none of the manufacturers have a super high heat performance version of the multi-zone. That will be here by next heating season, I'm told, for all of the manufacturers. This is just an 8-zone. It's one 4-ton, 48,000 BTU unit that can have up to 8 indoor units off of that one outdoor unit. And the one real difference with this one is that instead of having a spider web of lines coming from the outdoor unit, you basically go to a routing box and then from that box to a home run to each individual indoor unit. Do these things heat? Is it practical? Is it realistic to use them for heat and climate like something like Vermont? Yes, it actually is. And up until recent times, it really wasn't. Even when these things were designed, they've been in Japan for 30 years plus, but they didn't really design them this way in Japan. Japan doesn't have any climate zones equivalent to something like Burlington, Vermont. So it was really an add-on for the global market that they really thought of these things. If you look at this first line right here is the heat performance versus outdoor temperature of a conventional system. That purplish line represents a conventional single-speed heat pump that you would have the olden days, the one that gave heat pumps a bad reputation back in the day. And so what you'll see is when you get down to the teens, these things basically cease to heat. They're basically down to half of their nameplate capacity, half of the heat that they're supposed to deliver, they're delivering now when you get down below 20. And then they typically lock out below that because they can't actually continue to operate safely without damaging the compressor. Now you look at the hyperheat or whatever the various manufacturers call that type of product, and that's all of these lines up here. And you look at that, your full heating capacity down to about 5 degrees outdoor temperature, and then even down at negative 13 Fahrenheit, we're looking at about between 60 and 80% of its nominal capacity. So really substantial heat down at these temperatures. And they're designed to continuously operate this way. It's not like you can operate like that for a few minutes and then they're going to have to cycle or kick out or anything like that. They can continuously operate down to these very cold temperatures. Just one quick case study. This is actually from the Northwest. This is a third-party study done by NEA, which is the Northwest Energy Efficiency Alliance. And this was one of the systems that we're talking about displacing as much fossil fuel as possible. It was a 12,000 BTU unit, and they put it central to like the family room area, and they gave some operating data. This is a really busy slide. I'm not going to go through the details of it, but the real point of it is that this temperature trend line is down around negative 20 right there. And not only is the system still operating, but we're seeing COPs in the 1 to 2 type range. COPs are the blue dots. They're spread all around. You have to kind of average them. But negative 20, system's still operating, and relatively good COPs, as Peter described, COP being in relation to how efficient electric resistance heating would be. So a COP of 2, we're twice as efficient as a toaster oven, essentially, for heating. Lastly, the manufacturers have tools available. So if you guys are looking to compare, maybe someone's thinking of, hey, I'd like to see if it's a viable option for my home, want to find out how much it costs or what the operating cost would be versus some conventional systems. One way that you can do it, and this is just on paper, this is that seasonal COP. Because a COP is just a snapshot at a specific temperature, at a specific operating condition. So if you look at your COP at all your different temperatures, and this is just the weather bin data. It's 20 years of average weather data for Burlington, Vermont. And then next to it, I've got a COP at those various temperatures, the number of hours that we spend in each of those temperature bins each year, and you just do a weighted average. This one comes out to a little over 3. That's a little bit aggressive as a seasonal COP. I'd probably go with something more conservative. Most of the third-party studies that we've seen have been more like 2.5, a COP of 2.5 or 3. I've seen them as low as 2. Again, it's somewhat product specific, it's job specific, it's the home in which you're putting it, it's the way in which you use it. But if you use a seasonal COP of something like 2.5, that's a pretty good estimate. And what you can do is you can compare that to conventional systems. I think Peter did a really thorough job of explaining how do I compare this to oil or propane or natural gas, that sort of thing. A short way of doing that is the manufacturers have tools where you can just input how much you pay for oil, how much you pay for gas, how much you pay for propane, and it'll show you this sort of thing, a comparison. In this case, we just put in COP of 2, 3, 3.5. If your weighted average COP is something like 2.5, it's going to be somewhere in between those two bars right there. I mean, you can plug in whatever you want. And basically, you can just look at what the value is. This was done with 17 cents a kilowatt hour, which I think is appropriate for Vermont as a blended utility rate. $1.50 a therm for gas. Again, that varies depending on how close you are, and where you're located, essentially. Oil, that was $3.50 a gallon. Propane, $3 a gallon. I just did a study for just outside New York City, a White Plains area, where they were buying propane at $1.79 a gallon. That really affects how the energy comparison comes out. So how much you pay for fuel and those sorts of factors and what product you select kind of comes into this comparison. But just keep in mind, your contractors, your manufacturers, they have this sort of stuff available. They can give you these tools. If you're not comfortable using them, they can use them for you and help you through it.
We're from VSECU, so we're a credit union, and we're statewide. Some people remember VSECU as being Vermont State Employees Credit Union. It used to be just for state employees, and that's changed now, and it's everybody who lives or works in Vermont is eligible for membership. And what makes VSECU so attractive for a lot of people who are looking into financing efficiency upgrades, and that means everything from an audit to the retrofit work, a solar installation, a heating system upgrade like heat pumps, is that we're able to offer extended terms and lower loan rates on our products. So we have an environmental mission statement that we adopted in 2005, and it says VSECU is committed to finding opportunities within our daily business operations and product offerings to promote environmentally sound choices for our employees and our member owners. So in order to live up to that mission, we developed a whole suite of products that everything from a mortgage to a green vehicle loan, home improvement mortgages or loans, and Lisa will just talk a little about those. And they're great because a lot of people have been able to take advantage of them since we started in 2012, in June of 2012, and since then we've done over $5 million in loans. So it's been a really fast-growing program. VSECU also has a full-service commercial department called VBiz. So, you know, if you've got a nonprofit, you know, even a town or a business looking into doing some efficiency upgrades, we also offer a kind of a customized approach for those loans as well. So we're set up over next door, and I'm just going to give Lisa a couple of minutes to talk about what the options are. And then we'll get back to the technology because we know that's what you're really here for.
Thank you, Lori. Thank you, Lori. So with VSECU, we do offer, pardon me, an array of products, loan products primarily to help fund these types of improvements. And they can vary between a personal loan or a loan that's secured by your home. And that can be in the form of a home equity line of credit, home equity loan, or an energy-efficient mortgage. We do also finance off-grid properties. So the thing about mortgages and loans in this present lending climate is they're very specific to the situation. So I don't want to take up a lot of time going into specifics around requirements and such, but I'd love to speak with you as individuals at any point. We'll be next door, and we also have our cards. I work at the office right here in Brattleboro by Price Chopper, so we're accessible there as well. Thank you.
And then everyone will be right next door at the exhibitor room, 2 West. So go ahead and maybe direct your question to...
What's the refrigerant that's being used in these newer units?
R410A, which replaced R22 via the Montreal Protocol, which was an international treaty the U.S. is signatory of.
And that's essentially going to be piped through walls for a...
Yeah, so instead of moving water or air to condition your home, you're moving refrigerant. It's no different than anyone who has central air. It's just with central air, it only works in cooling mode. With a heat pump, you have a reversing valve. Imagine a wall-mounted, a window unit that you have for air conditioning. Well, what if you turned it around the other way? Now it's putting heat out the other way. And these systems are just a reversing valve that moves the refrigerant the opposite way.
And are the conduits insulated to preserve
Oh, the pipe, yes, the piping is all insulated, yep. And if it has to go underground, then there's weatherproof tubing and everything, like PVC type tubing that you would use, and all sorts of guidelines.
John?
Moderate to low end of the insulation scale, and so typically this technology is going to be best suited for your moderate to well insulated infrastructure. Not to say it can't be used in that, it's just not the ideal application. There's also a variety of indoor units. You could use perhaps a ducted unit or a ceiling cassette, like for this type of ceiling. So it doesn't have to be a wall-mounted unit. There's a variety to choose from.
Yeah. But I'm going to be having an energy audit done, so I'll find out what I can do to correct a lot of it.
I'll let you folks make the... Back to the cost. Do you have any idea what it might cost to heat a large building that was, let's say, 100,000 cubic feet?
So we're saying a commercial building?
Yeah.
Okay. As compared to what? Or you're just saying, okay.
As compared to dollars?
So,
I mean,
I do a lot. I'm a mechanical engineer, so I do a lot with energy and loads and that sort of stuff. So typically, ballpark national averages are, for a commercial building, $1 to $1.50 a square foot is your total energy consumption for the building. That's including lights, plug loads, HVAC. So of which, in a commercial building, 40 to 60% of which is typically your HVAC. And again, that's going to vary enormously. An office building has very little outside air requirement. A school has a lot of air, outside air. And so that 40 to 60 range is going to be different on those two. The manufacturers also have different tools where you can plug in this and it'll give you an estimated annual operating cost where you can put in that it's in a school occupancy. 100,000 square foot, the weather file to choose from in Burlington or wherever, and it'll do that sort of stuff. As compared to conventional fuels, you're looking at approximately 50 to 60% energy cost reduction over oil. Again, it varies to how much you pay for energy, and over propane, even a little bit more than that.
I said 100,000 cubic feet. Not square foot, not a square feet.
About 10,000 square feet. About 10,000 square foot, okay. So, I mean, you can factor, maybe 60 cents a square foot or something for annual operating costs of the HVAC. But again, I mean, it's really job specific. That range is 60
Sure.
cents a square foot, plus or minus 60 cents a square foot, Really, to be honest.
The way you can just calculate the heating load. It's not too difficult.
That would be
the exact heating load for that building, given the.
But the square footage doesn't. On average, you're looking at 400 square foot a ton is your sizing, and 40 BTUs per square foot, and that could be a quick way of calculating it, and then determining how much energy would be used for that. Sure.
How frequent are the defrost cycles?
As needed. So the defrost cycle actually just initiates based on coil temperature. It's not just a dumb time sequence. It'll actually go, and all the manufacturers, to my knowledge, do it the same way. If it says this coil is sufficiently cold for a certain number of minutes, defrost initiates. All defrost is reverse cycle. Now we're sending heat to the outside coil instead of cold refrigerant. So now it starts thawing the coil until that coil reaches a specific warmer temperature. When it reaches that specific warmer temperature, it comes out of defrost. So if there's tons of frost on the coil, it's going to take 10, 12 minutes for that coil to defrost. If that coil doesn't have any frost on it, even though defrost initiated it, it'll come right out of it in a minute or two.
And the technology in the coil has changed too, because now they have this what they call a hydrophilic coating on there. So now, as soon as there's a little bit of moisture, it pops the frost off. So now, from 10 years ago, our defrost cycle now is more than cut in half, because we're expelling this frost pretty quick. So, but if you sit there, Joe said, just go there and sit there and watch it and see what it's doing. You're never going to make rhyme or reason why it's doing it. It's going to decide. It's a smart machine.
12 minutes is about the maximum too that we typically see. It varies a little bit from product to product, commercial to residential, but you're never in it for more than about 12 minutes. There's onboard controls in a lot of the units where you can actually have it, if you have an auxiliary heat source, you can have the indoor unit tell the auxiliary heat to come off when I'm in defrost, just as a controls integration thing. That takes a little bit more cost on the front end for a project.
And then you have the other thing where the unit, so you don't feel cold air, the evaporator is going to make sure to slow the fan down. So we never want to discharge cold air in the space we're trying to heat. So we're slow the fan down as much as we can, and then reverse cycle that.
Bottom line, if you use the manufacturer's tools to design your system, you'll be safe. So for instance, the software tools that we use to design these systems, they actually take into they take into account the maximum defrost that you could possibly have. So if at a specific temperature the maximum defrost is 7%, that's what it's going to use in the tool on its approximation. That 7% is at 100% RH relative humidity. It might not be that condition outside, it might be less than that. So it really, the numbers published in the literature are extremely conservative, and you can design. Yes, sir.
I heard him mention something about it serving as an air, the fellow had one in his house, serving as an air exchange. If it's serving as an air exchanger, where you don't need heat and you don't need cooling, can it run as an air exchanger, the wall-mounted units or any of the units, to exchange the air in your house in a tight house or tight, well-insulated house?
That's
In
not
other
what
words,
he said.
you don't need cooling or heat, can it serve as your air
Like an HRV or an ERV, an energy recovery ventilator?
Yes.
That's a separate product, because that has to be ducted to the
right.
outside and from the zone.
So to answer your question, potentially yes.
Yeah, it can be
That's
integrated
what
to the system.
he was saying, that it was kind of serving as an air exchange.
No, it's
Yeah, it's a separate product that integrates with these products.
Mike, did you have a question?
Oh, I was just saying, though, the heat exchanger is transferring energy from a liquid, which is the Freon, to the air in the room. That's the heat exchange. But it's not an air exchanger where you're taking outside air and bringing it in and exchanging it with fresh air. These systems don't transfer any air from the inside to the outside. The only thing that moves from inside to outside is the Freon back and forth between the refrigerant filters that connect the indoor and outdoor unit. So there's no airflow between the inside space and the outside space.
Yeah, Mike, I thought you had a quick question. I thought your hand was up a little while ago.
I did have a question about the defrost and the fan speed.
All right.
So if you wanted to start, say, with one of the systems where you have one pump outside, and you have one wall unit inside, and later on wanted to go to multi-wall units, are you talking then a whole replacement of the system, or not?
I can only speak for, I'm not sure what they, like on ours, if you're doing what they call an 18,000 V2 dual zone, we got to have at least 2 evaporators hooked up to it. You start getting into a 2-ton, 24,000 V2 outdoor unit, you can have 2 zones hooked up and hook the third up later on. 3-ton, the 36,000, same type of thing, and the 4-ton, 8-zone, same type of thing.
So long as you have a capacity in the outside unit, you could...
You got to meet your minimum requirements for that particular condenser.
Same for us. The one caveat there is, say you got like a 3-ton outdoor unit, and you've got 4 tons worth of indoor units connected to it, that outdoor unit can still only produce 3 tons. And the whole point is that you're not going to use all those indoor units at the same time. It gets spread, the refrigerant gets spread equitably among them if they're all powder. So.
Yeah, we're relying on load shifting. If the sun isn't going to be on that side of the house when these things that. So it's a nice feature that came up, technical capacity.
It's nice if, you're down in the living room area for heating, and then when you leave the living room, you either set that unit back or turn it off, and then you go to the bedroom areas at night, but you don't have them both on full blast at the same time. Yes.
How much noise do you actually make, and is there annual maintenance or servicing that's required?
The noise is probably the most dangerous question that I can possibly answer. I will tell you on paper, we are absolutely quiet. I live with them. I can tell you from my perspective, they're absolutely quiet. But and they are, relatively speaking. Some people are, you put one in a bedroom, then maybe it's quiet for me, but not for you. The decibel rating on these things are very, very low. Even the outdoor unit is very, very low. But the problem is that noise is potentially a subjective thing from a consumer standpoint. So that's the deal. As far as maintenance goes, these are a split system. And what I mean by that, there's an outdoor unit and there's an indoor unit. If you want to maintain efficiency, you should be cleaning your coils. Right?
Clean your coils and change your filters. I mean, that's really the only maintenance. There's no schedule.
There's not a huge event where you got to want to start changing capacitors and doing this and that and the other thing. It's a pretty simple process. But, it should be.
Is the homeowner doing that?
I'm sorry?
Is the homeowner doing the cleaning of the coil?
Typically not. Typically they're not. The filters, yes, absolutely. From my perspective, yeah, filters are no problem. But sometimes you clean the indoor coil. If it's been in for a few years and it's time to clean that fan and stuff, typically the consumer is not going to get involved in that process. It's a little bit cumbersome.
The only time it's really an issue is if you don't clean the coils for a really long time and you don't change the filters. Well, as soon as the filters are clogged, air is going to take the path of least resistance. It's going to find a way around that filter. When it's around that filter, it's going to hit the coil. If the coil's wet, now you have cement. It just becomes, and that's the same for any air conditioning equipment. It doesn't matter if it's a rooftop unit or anything like that. So just, changing your filters and cleaning your coils, on a 6-month basis or year basis, not on a every 5 years.
Yeah, if there's like 5 cats in the house and 3 dogs, and it sheds a lot, then obviously you're going to clean the filters a lot.
Improvements. You mentioned improvements. It sounds like this is moving pretty fast. But can you say any more about that?
Exponentially. The technology coming out, we're probably not going to recognize any of this stuff in 10 years.
R&D cycles are about a year. We're saying new product every year, and it's about on a per weight basis. If you compare it to its American counterparts, your York Carrier Train products, it's about 30% lighter, about ton for ton, and so that 30% equals better. And each generation of product gets a little bit bigger and a little bit heavier. Well, each time it gets larger, those COPs go up, the seasonal efficiencies continue to climb with it. So you'll see higher efficiencies, you'll see better heat performance, you'll see better controls. That's another area.
And you suggested that the most efficient units may have multiple connections, whereas they do not now. Did I hear that right?
Not necessarily. Some of the most efficient products are just one-to-one systems. It really depends. Efficiency on paper versus efficiency in the application too. It's a little bit different. But to be honest, the way I generally tell people to look at this stuff, is it a variable speed heat pump or is it something else? In looking at comparing one variable speed heat pump to another is really difficult to do because then it becomes application specific. It's kind of a difficult thing to do when you need a lot of information about the application to do a good job of that. So typically comparing this to other technologies is the way I look at it.
I need to really bring this to a close because we billed it till 7:30. It is 7:30 now, but we also are making themselves available in the room right next door for further questions. I'd like to thank everybody.
Bye.